Start with a kind of high-level introduction to random unitaries and why we care about them. I'll try to go kind of fast because I think this is an extremely expert audience. And then I'll talk about what we know about random unitaries and what we learned from our paper. And please just interrupt with questions at absolutely any point. Cool. Okay. So at a super broad level, all of this is motivated by this exciting era of quantum science that we're currently in, where modern experiments are increasingly pushing beyond the traditional regimes of both quantum physics and quantum information and computation. And this raises lots of interesting questions in the field. For instance, how do we benchmark a large quantum device? How do large quantum circuits and Hamiltonians behave? How can we find quantum advantages, especially in near-term experiments? And a class of questions that will be especially relevant for this talk, what properties of a quantum state are easy to measure in experiments, and what properties might be fundamentally hard? And so in trying to answer these questions, there's been a surprisingly ubiquitous tool that has been very helpful. And this tool is the idea of a Haar-random unitary. So a random unitary on n qubits is just a 2 to the n by 2 to the n matrix drawn from the Haar measure on U2 to the n. And at first glance, if you haven't worked with these before, you might wonder why we ever care about such an object. Like, don't we normally care about some highly structured unitary implemented by some specific quantum circuit doing some computation of interest? Or don't we care about the dynamics of some Hamiltonian modeling spins and electrons in the real world? Why would I want to do a completely random thing on my entire 2 to the n Hilbert space? But nonetheless, we found lots of reasons to care about random unitaries in trying to answer these questions on the previous slide. And so I like to start this talk by just kind of very quickly running through a handful of the popular applications of random unitaries. Because I think, at least for me, like sometimes I'm more familiar with some than others, but there's actually lots of reasons throughout the field. And so I'll group these into several different classes. And the first class is random unitaries as an application. So instances where I actually want to apply a random unitary on a quantum computer. And so one of the hallmark instances of this is classical shadow tomography, which is a kind of very interesting protocol for doing fidelity estimation on quantum states. So say I have some quantum state in my lab, and I want to measure the fidelity of that state with respect to some target state. You know, maybe the state I was trying to prepare, and my actual state is some noisy version of that. And say for some reason that just directly measuring this fidelity is hard. Maybe that target state is a little bit complicated. Well, there's this very cool protocol for estimating fidelities, where instead of just directly measuring a fidelity with respect to the target state, I take my quantum state in my lab, I apply a random unitary to it, and then I measure in the computational basis. And then I draw a new random unitary. I do this again and again and again. And they show that after a surprisingly small number of times, this allows me to estimate the fidelity of my state with respect to any target state I so choose. And so this is an instance where doing a random unitary actually achieves a large advantage over other protocols that don't involve doing a random unitary. Another instance where I actually want to apply a random unitary in my device is in quantum supremacy experiments like random circuit sampling. And in particular, our best arguments for the classical hardness of random circuit sampling rely on the resemblance of random circuits to random unitaries, specifically through this property called anti-concentration. And there's been a lot of recent excitement over random unitaries being applied in quantum cryptography. So intuitively, a random unitary very efficiently hides quantum information. And there's been lots of interest on whether we can design cryptographic protocols around this fact. And this brings me to my kind of second class of reasons for caring about random unitaries, which is as a toy model for complicated processes in quantum many-body physics. And so this has been very popular in the last decade or so in many-body dynamics, where in many-body dynamics, we have lots of specific Hamiltonians and circuits we care about, but these circuits are often very hard to study exactly, either numerically or theoretically. And so there's been a whole line of research on kind of modeling properties of physical systems by random unitary circuits. And there's been a whole field of research on, trying to understand universal phenomena in many-body dynamics with random unitaries and random circuits. Random unitaries have also been a very useful toy model in quantum machine learning, especially in understanding challenges in training quantum machine learning models. And also a really key tool in our modern understanding of the ADS-CFT correspondence. So it turns out that lots of the most paradoxical and surprising features of this correspondence can actually be understood as just surprising but fundamentally quantum mechanical properties of random unitaries. And so if that wasn't enough, I have kind of one more reason why we care about random unitaries, which is as a counterexample. And so this harkens back to that question in the first slide, which was what properties of a quantum state are easy to learn from experiments, and what properties are fundamentally hard. And in particular, a lot of progress in understanding what properties are hard has come from our knowledge of random unitaries. So the general strategy is if I want to prove that some property of a state is hard to learn, I pick a completely random example of a state that has that property. And then using tools from random matrix theory and random unitary theory, we can often provide rigorous lower bounds on how hard it is to learn that property in that example. And so this has underlined a lot of the progress in quantum learning theory in the last couple of years. And so with all these applications in mind, there's one really central question to all of them, which is in what circuit depth can a local quantum circuit look like a Haar random unitary? And I'm sure you all know this, but a very naive answer to this question is very pessimistic. So a true Haar random unitary with very high probability has exponential depth in the number of qubits. And the reason is just that there are many more deep quantum circuits than there are shallow quantum circuits. So if I pick a random quantum circuit, it's very likely to be deep. And what this tells us is that any useful answer to this question, in what circuit depth can we form a random unitary, any useful answer requires some notion of approximation, where maybe I am not exactly implementing a Haar random unitary, but I'm implementing something that's just as good as a Haar random unitary for all intents and purposes. And so people have come up with basically two notions of approximation when considering random unitaries. And these are known as unitary K-designs and pseudo-random unitaries. So I'll start with the first, unitary K-designs. These have been around a very long time at this point. And kind of roughly speaking, a unitary K-design is some ensemble of unitaries, where if I draw a random unitary from this ensemble, it is indistinguishable from a Haar random unitary in any experiment that queries U up to K times. So K is some parameter. And so, kind of drawn this at the left. So I'm imagining some experiment that prepares a completely arbitrary initial state psi, applies the unitary, does a completely arbitrary quantum circuit, applies the unitary again, does an arbitrary quantum circuit, and so on up to K times. And if U is indistinguishable from Haar random in any such experiment, then we call it a unitary K-design. I'll include a kind of more precise definition a bit later on, but this is kind of the intuitive and operational definition of unitary K-designs. So this is great. But more recently, people have started thinking about a slightly different definition of approximation, which is known as a pseudo-random unitary. And pseudo-random unitaries are kind of stronger than K-designs in some respect and weaker in others. So an ensemble of random unitaries is a pseudo-random unitary ensemble. If when I draw a random unitary, it's indistinguishable from Haar random by any efficient quantum experiment. And here by efficient, I mean polynomial time. And so what this means is, so a polynomial time quantum experiment can query U up to any polynomial number of times. So K, intuitively, this K in the unitary K design can be any polynomial in N. And so this is very strong. It's like letting K be extremely large. And so in exchange for that, I have to weaken the class of quantum circuits I consider. So I demand that in these experiments, each quantum circuit and state is created by a polynomial depth quantum circuit. So I query U any polynomial number of times, and in between it, I do any polynomial quantum circuits. And if U is indistinguishable from Haar under this criteria, then we call U a pseudo-random unitary. And just a brief note, so when we're proving that something is a pseudo-random unitary, we need some assumption on what is the power of a polynomial depth quantum circuit. And so we typically prove that something is a pseudo-random unitary under some standard cryptographic assumption about the power of quantum circuits. Cool. And so with these definitions, people have gone off and tried to prove that various ensembles are unitary designs or are pseudo-random unitaries. And in particular, trying to generate these objects in as low a depth as possible. And so I just want to kind of very briefly recap the state of the art on both of these questions. So for unitary designs, the best constructions of unitary designs come from local random circuits. So say a 1D chain and just local random gates, Haar random gates, applied in some brick pattern on that chain. And it's been shown that local random circuits form unitary K designs after a depth roughly K times N. And this holds in 1D, but also many other circuit geometries.
Can I ask a question?
Yeah.
Like when you consider like random circuits, of course you mean like unitary K designs in the sense of approximation, and is the sense of approximation always the standard diamond norm sense, or is it a different sense? Because like there was, for example, this thesis of Richard Lowe of Bristol, who's looked into different fine prints of different sense of approximation, and then in the meantime, I think people usually mean diamond norm. But are you coming to that, or is that something?
Yeah, I will come to that. Basically, we're going to use relative error in our work, which is stronger than diamond norm. And yeah, this result I'm stating here also holds for relative error.
Wonderful. Thanks.
Yeah. And so in particular, many of you know this, but this linear and n dependence was found quite early on in this Brandau-Horodecki work. And then there's been kind of a relatively large series of recent works that are successively improving the K dependence, including, two very nice ones by Jonas. And so the final most recent result has a linear in K dependence up to some log factors, which we know is optimal. And I want to pause just very briefly to note that this result on its own is already very remarkable, because a true Haar random unitary requires exponential depth to implement. And now we're showing that just some simple local random circuit is indistinguishable from a random unitary in a much, much lower depth, just linear in n instead of exponential in n. Okay. And so moving on to pseudo-random unitaries. So again, this progress is all much more recent for pseudo-random unitaries. But in particular, this work by Fermi Ma and Robert Huang from a few months ago proved that something called the PFC ensemble forms a pseudo-random unitary ensemble. And this was our first construction of pseudo-random unitaries. And so I don't need the details of this very much for this talk, but I'll just briefly describe it so we're all on the same page. So the PFC ensemble was something proposed in this earlier paper by Metger et al. And it's a product of three big quantum unitaries. So first, we do a random Clifford on all n of our qubits. So just draw a random unitary from the Clifford group on all n qubits. Then we do something called a random phase gate. So this applies a random plus or minus one to every computational basis state. This is the F in PFC. And then we do a random permutation gate. And the permutation here is specifically over the 2 to the n bit strings. So it's something that takes in a bit string and spits out a bit string, and permutes them in some maximally random way. And in reality, these P's and F's are actually called pseudo-random permutations and pseudo-random functions, and we rely on some existing results showing that there exist pseudo-random permutations that are indistinguishable from truly random permutations. And so then the final result of Ma and Huang is that if I do this unitary, so I take a random Clifford, a pseudo-random function, and a pseudo-random permutation, and I apply that in any experiment, it is indistinguishable from a Haar random unitary as long as that experiment is polynomial time. And again, the details of this will not be important for our work, but because we do use this result, I wanted to describe them a little bit. Okay, and so if we know this thing is a pseudo-random unitary, we can also ask what depth can we implement this? And it's known basically that in a 1D circuit, we can implement this PFC ensemble in polynomial time. So we can implement the C, the F, and the P all individually in polynomial time in 1D. It turns out we can actually improve this quite a bit in all-to-all circuits, so circuits with very non-local 2-qubit gates. And in those circuits, we can implement the PFC ensemble in polylog depth. So we get some exponential improvement from having a very non-local connectivity of the circuit. And so, yeah, again, in 1D, this poly n is kind of roughly comparable to this linear depth for the designs. And then we get some exponential improvement if we allow very non-local connectivity in our circuit. And so this is the kind of best known results for unitary designs and pseudo-random unitaries. Yeah. And I just want to remark that I think for a long time, we all thought that these circuit depths seemed very reasonable. So for example, in 1D, circuits require linear in n depth in order to generate high entanglement across any cut, or to have an extensive light cone, where some bit flip on an initial qubit affects all of the qubits at later times. And high entanglement and big light cones are both properties of Haar random unitaries, so it seems reasonable to expect that a unitary design should satisfy these properties, which would mean that we need linear depth to form designs. And by similar arguments, one can actually rigorously show that classical circuits require linear depth in 1D to form pseudo-random circuits or designs. And the argument is extraordinarily simple. We just consider applying our classical circuit to two input states, so two bit strings that differ only on the first, the leftmost bit. So say the all zero string and the all zero string with the first bit flipped to 1. And if this circuit is very low depth, then within the light cone of this first qubit, these two input bit strings will output very different bit strings inside the light cone because we're doing some random gates. But outside the light cone of this first qubit, the output bit strings have to be identical because the input bit string was kind of identical on the region that could influence this output region. And so with this very simple argument, you can very easily distinguish a low-depth classical circuit from a truly random classical circuit by just checking if all the rightmost bit strings are the same. And so in our work, we show that something very different happens for quantum circuits. And so I'll start by just stating our results, and then I'll give some intuition and show how we prove them. So our first result shows that local random quantum circuits form unitary K designs in depth order K times log n on any circuit geometry. So the same linear and K dependence as previous work, but exponentially improving this n dependence. And yeah, so here's the brief remark on the notion of error that we use. So the notion of approximation error. We use this notion called the relative error, which is a little funny to define, but the kind of take-home message of it is that it's a very strong notion of error, because it says that the output of any experiment that queries U from our ensemble approximates the Haar value up to relative precision. So even if the Haar value is exponentially small, for instance, our ensemble captures that value up to a small relative error. And this is useful in some applications. And this is strictly stronger than some other more familiar notions of error, such as the diamond norm, etc.
Can I ask a question?
Yeah.
How the dependence of the error epsilon, your relative error epsilon, enters in the depth?
Yeah, so the depth will be K times log n over epsilon. So the n over epsilon is both inside the log.
Okay, thanks.
So yeah, logarithmic dependence on epsilon. Yeah, Jens?
Now, can I ask another question? Because now we are interrupted anyway. Yeah, I'm aware from Jonas that it works for any circuit geometry, but you still consider log depth random bricklayer circuits, right? So there's kind of some regularity assumption on the underlying graph, I guess.
Yeah,
are there any limits, or is that basically like any regular graph does that graph does a drop, and then you just have to have a log depth
yeah. So
bricklayer on top of that?
So what we prove basically is it applies to any geometry with very few assumptions, but it's essentially what we do is we construct it in 1D with a fairly natural seeming circuit. And then to show that you can generate unitary designs on any geometry, we just show that you can kind of snake a 1D circuit in some particular way on any geometry. So
okay. And it induces some very mild assumptions on the regularity of the problem. I can see.
Yes, exactly. But it's maybe in 1D, it's kind of a relatively natural local random circuit ensemble. In other geometries, it might look a little bit funny. We're just trying to prove that you could, in principle, form a design in this step.
Wonderful. Thank you.
Can I ask another question?
Yeah.
Yeah, sorry for that. I mean, I didn't deeply think about it just now, but doesn't this result contradict the fact that you can learn circuits with log n gates in poly ensembles?
Yeah, that's a great question.
Besides, it's by the same author, right? Overlapping author.
Yeah, by Robert. Yeah. So Robert and Yun Chao have this paper that shows that you can learn a circuit of depth D with resources that are basically exponential in D. So for log, if D is log n, then the resources are polynomial. This doesn't contradict it. It kind of like actually perfectly closes the gap where all of the circuits they can learn are just below our result. And just above the circuits that they can learn, we can prove that things are hard to learn. To show this, it's more clear when I discuss pseudo-random unitaries. For designs, one thing I'll note is that our depth is linear in K. So if they can learn it from polynomially many samples, that requires taking K to be polynomial in N. So the unitary design result actually has no implication on showing hardness of their learning algorithm.
Yeah, no, true. Yeah, thanks.
Yeah, but the pseudo-random unitaries, which I'll get to in a second, those will kind of close the gap on their construction.
Okay, thank you.
Yeah.
It's funny because actually I was asking myself the same question a couple of days ago, and I was basically following the same logic because I also thought it's kind of quite natural, this thought.
Yeah. Cool.
And,
So yeah.
Sorry. And any geometry include also all-to-all connectivity?
Yes, it does. It becomes like a yes, it definitely includes all-to-all connectivity because with all-to-all you could just draw a 1D circuit with your you could use your all-to-all to implement a 1D circuit and then
So
you
you
could
random,
it's not like the most natural random circuit you would define for that connectivity. We just prove that a circuit exists that you can implement with that connectivity.
your result is more there exists a distribution of circuits such that they form K design, but not that random circuit you would draw.
Yeah, exactly.
Okay. So you mean a fixed architecture, you apply, okay,
Yeah.
it's not,
So
okay,
for-
all-to-all, I meant maybe that you sample randomly the position of the gates as well.
yeah, we don't analyze that. Yeah. And even I'll get to it, but even our construction for 1D is not just a strict brickwork 1D random circuit. But okay, I'll first state the results and we'll get to all of these. So our second theorem concerns pseudo-random unitaries, and we show that quantum circuits can form pseudo-random unitaries in depth polylog n in 1D circuits and polylog n in all-to-all connected circuits. So again, kind of similar to the design result, both of these depths are exponentially better in n compared to what was previously known. And just to comment on Robert and Yunchao's result here, so they show that you can learn a 1D circuit up to log n depth in polynomial time, and above log n depth, it becomes first quasi-polynomial and then, exponentially harder as you increase the depth. And our result basically shows that this has to be the case above some polylog n depth. So above some depth polylog n, your complexity of learning a circuit has to be at least super polynomial in n. So they can learn it up to log n, and just above log n, it becomes hard.
Do you only assume one-way functions, or what's the?
Yeah, so our assumptions are identical. We don't need anything new. We just assume that the PFC ensemble essentially is a pseudo-random unitary. And yeah, fundamentally that draws back to the existence of quantum secure one-way functions. Yeah.
And yeah, or are there other interesting settings in between? Like 1D is special enough, then of course all-to-all is particularly attractive, and then poly log is very, 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 very shallow. But
Yeah,
do you have other examples that are somewhat intermediate?
Yeah, it would. I mean, for example, it would be great to know what happens in 2D, whether you can do better than 1D. We don't know. We've tried to think about it, but the tricks we have do not apply there. So that's an open question.
So basically, do your tricks work?
What is the exponential in the polylog?
Sorry.
What's the exponent in the polylog?
Oh, yes. I don't know, actually, is the answer. Typically, so again, this depth comes back to how fast you can compile the P and F in PFC. And this draws back on some old cryptography papers in classical cryptography, and they are not very tight with their bounds on the depth. And so we did at one point think about trying to go through their analysis and getting the precise polynomial, but we haven't done that yet. So yeah, it's polynomial, but I can't tell you the precise degree.
Right.
Yeah. Cool. And so, yeah, just is there another question?
Okay, maybe I ask later. Maybe you will answer.
Okay. Yeah, I'll get to all of the details of all of this. I just wanted to state things first. Cool. So yeah, just kind of like a high level comment. These circuits are shallow. They have very low complexity and only local short range entanglement. And yet our result is that they're indistinguishable from unitaries with exponential complexity. And so I wanted to start by just giving some very rough intuition as to why this is possible, and then I'll tell you how we prove it. And I'll tell you precisely what our construction is. But I wanted to start by just showing why this classical counterexample breaks down in the quantum case. And fundamentally, the rough intuition is that quantum circuits, unlike classical circuits, they can hide information locally into non-commuting observables. And so to illustrate this, I want to just kind of step by step look at what's happening in a classical circuit and a quantum circuit. So in a classical experiment, we prepare some local information, some initial bit string. We then evolve that bit string under my classical circuit of interest. When I do this, the local information, say about a single bit in my input bit string, is delocalized over like xi bits of the output bit string, where xi is the depth of the classical circuit. And then at the end of my classical experiment, I measure all the bits in the z basis. And a really crucial fact here is that my information is spread into classical observables. So because the circuit is classical, initial information in the z basis is spread to other information in the z basis. It might be more delocalized, but it's still in the z basis. And what this means, practically speaking, is that by looking at the output bit strings, I can always see, for instance, that the two input bit strings differed at one of their bits, because this difference manifests in some z observable on the output bit string, and I can see that that observable is different between the two. And I can also see that very far from this flip bit, the output bit strings have to be the same, because all of the initial information about this state is the same between my first and second input bit string. And so because all of that information manifests in the output, my output bit strings also have to be the same. So this might sound a little tautological, but it'll make more sense now when we go to the quantum circuit. So in a quantum experiment, I start very similar. I prepare some local information, some product state, say, and then I evolve that state under the quantum circuit. And when I do this, the local information about some qubit in my initial state is again delocalized into xi qubit observables, where xi is the depth of the circuit. And then at the end of my experiment, I measure my system in some choice of basis. And the crucial fact here is that if I hide my information in some observable, and I measure in a basis that does not commute with that observable, that information is invisible to my measurement results. So if I store some information, say in a coherence, like a Pauli observable with an X in it, and I measure in the Z basis, that information does not influence my measurement results. It just manifests as pure randomness in my measurement results. And so like at a very rough level, what's happening in these low depth random unitaries that we construct is that they're hiding information into random local observables. So if we have some depth D circuit, I'm hiding information into a random depth D observable. And the crucial fact is that most say xi qubit observables do not commute with each other. So if I choose a random observable on say log n or poly log n qubits, with very high probability, this observable does not commute with any fixed choice of measurement basis. This probability vanishes exponentially in the number of bits my observable acts on, so the depth d. And so if I make that depth d just large enough, just like logarithmically large to make this probability very, very small, then with very high probability, my output measurement does not reveal information about the input state of my experiment. And very roughly, this is what's allowing quantum circuits to appear random in a much lower depth than classical. Yeah.
Can I ask a question, or it's like more like a meditation than a question? So I apologize if it's a bit vague, but So this, when you're very convincing in explaining like why the non-commuting character helps a lot, like of the quantum setting over the classical setting. That
Yeah,
is
yeah.
completely by this. At the same time, it's true that if you look at 1D circuits, it can help if you want to get a global unitary design to play with the probability measure of the local gates and look at non-Haar random circuits, so that
Yeah.
while they're seemingly less random locally, then they still give rise to better designs.
Yeah,
So,
yeah.
but then they might not be fully Haar random locally. So why does that intuition not contradict your intuition that you want to be as non-commuting as possible, which would mean that the obviously optimal choice would be locally Haar random, like little bricks in your circuit.
Yeah, I
This doesn't
think
really fit together in my head. Can you help?
yeah, I think it does fit together in the end. So the way I understand this result on using not Haar random gates is that you use gates that spread your information as fast as possible.
Yes.
And what that, okay, so like no matter how random your circuit is, if your observable only acts on like 10 qubits, it can only be so random on those 10 qubits and so non-commuting. But if you now design a custom circuit that scrambles it to 15 qubits, there's a lot more observables on 15
I
qubits.
understand. Yeah, that's a good thing. So it's like it's the non-commutativity, but it's also the kind of speed of information spread kind of that matters. And that
Yeah.
together gives you a trade-off. Okay, I think that's a great answer. Thank you. For a vague question, a very, very precise answer. Very
No,
good.
no, I wondered it myself one time.
Yeah.
Okay, cool. So this is just some like very kind of vague, rough intuition for why quantum is very different from classical. And now I want to actually tell you, what is our construction of low depth random unitaries and how do we prove our result? And so you might have noticed that like we had all these three different scalings of the depth, and in every case we achieved exactly an exponential improvement in the dependence on n. And the reason is that all three of these results come from one very simple and general approach to exponentially reducing the depth of a random unitary. And so our approach is as shown here. We consider an ensemble of random unitaries that's generated by a two-layer brickwork circuit that I drew here. And so just to describe this, in the first layer, we arrange our qubits on a 1D line, and we group the qubits up into patches of polylog n qubits each. And then in the first layer of our circuit, we apply a random unitary drawn from some ensemble on the first patch, and on the second patch, and on the third and fourth, and so on. So that's the first layer of our circuit. And then in the second layer of the circuit, we do the exact same thing, but shift it over by half a patch. So half the qubits in the first patch get connected to half the qubits in the second, and the second to the third, and so on. And after this, we stop. And this is the ensemble that we consider. And so just to state our main results in a more precise way, our first result shows that if each small random unitary in this two-layer brickwork ensemble is drawn from an epsilon over n approximate k design on roughly log n qubits, then the entire circuit forms an epsilon approximate k design on all n qubits. And so what you can imagine here is that each of these small random unitaries is some local random circuit acting on log n qubits. And now we know from earlier results that local random circuits converge to designs on those qubits in a depth that scales linearly in the number of qubits. So if I have log n qubits per patch, I can form a design on those qubits in depth log n. And so if each of these small random unitaries is a local random circuit of depth log n, then my whole circuit just has depth 2 times log n. It just has twice the depth of the small random unitary. And so our claim is that our construction basically just gives a factor of 2 on the circuit depth, but it exponentially grows the number of qubits from log n to n. And again, this epsilon approximate is this notion of relative error that I mentioned earlier. All right. And so our second result is very similar. So it says that if each small random unitary is drawn from a pseudo-random unitary ensemble on polylog n qubits, so just slightly more qubits, then the whole circuit forms a pseudo-random unitary on all n qubits. So again, each of these small random unitaries you can imagine is like a small PFC construction. And when we apply all the different PFCs in this fashion, we get a pseudo-random unitary on all n qubits.
Sorry?
And so, yeah.
The polylog here comes from taking epsilon equal 1 to the n to omega 1, or I mean,
Yes.
yeah,
the polylog comes because yeah, basically in this eventually when we prove something is a pseudo-random unitary, we'll reduce it to a question of whether some different thing is a design for any super polynomial k or super polynomial epsilon. And when we do that, we'll have some factor that's, say, like log 1 over epsilon. And if we ask for epsilon to be super polynomial in n, then log 1 over epsilon is kind of super logarithmic in n. So polylog would suffice. Yeah,
okay,
so that's
so it's enough to prove relative error in epsilon, and then basically pseudo-random unitaries is a corollary taking the epsilon. Yes, a
yeah,
superposed one.
yeah. You have to so you have a few steps to this. Basically, like this PRU so okay, the PRUs are involve pseudo-random permutations and functions. So what we do is we first show that the small pseudo-random unitaries are indistinguishable from small Haar-random unitaries. And then we use our design result to show that this two-layer circuit with small Haar-random unitaries is a relative error design with very small epsilon. So it's just to say the PFC ensemble itself is not a relative error design, but it's indistinguishable from something that is. Does that make sense?
Thank you.
Yeah. Okay. And so now I just want to kind of go over briefly how we prove this. Because in the end, at first it was kind of long and complicated, but in the end we boiled it down to a few pretty simple steps, which I think might be useful beyond just this specific application. And so the most crucial step is this thing we call a gluing lemma. And so the gluing lemma is as follows. Suppose I have an epsilon approximate K design acting on two subsystems, A and B, and a second epsilon approximate K design acting on two other subsystems, B and C. So, the designs overlap on B, but also have some disjoint regions, A in the first one and C in the second. And suppose I take UAB and UBC and I multiply them together. So that defines a new unitary ensemble acting on A, B, and C. And our result is that this unitary ensemble is an epsilon 1 plus epsilon 2 plus k squared over 2 to the nb approximate K design. So if you put in K designs with small errors epsilon, you get out a K design with just as good of error, plus a small correction that's like K squared divided by the number of qubits in the overlap. And you can kind of immediately see that this result implies our main theorem, because we just apply this lemma n times in a row. And after the first application, we kind of have glued together the first and second random unitary in the circuit. After the second application, we've glued this with the third random unitary. After the fourth, with the fourth. And we just proceed so on down the chain. And after applying this lemma n times, we've shown that the entire two-layer circuit is a unitary design. And the error in that final design we construct involves n times the input error, because we're summing up the error from every input unitary in our circuit. So this is why we required the input error to be like epsilon over n in the previous slide. And then we'll also get a factor that's like n times k squared over 2 to the number of qubits in the overlap, because we picked up this error k squared over 2 to the nb n times. And if the overlap of these qubits is sufficiently large, so nb is larger than log n times k squared, then this error, this additional error, will be very small. And so that sets the size of the patch that we need to consider. So this is how we prove it in 1D, but you can also readily apply this trick to lots of other ensembles, for instance, in 2D as well.
That's, by the way, the part that Scoop does, but never mind.
Oh,
Don't worry, fine.
So because I assume there are some experts on random unitaries in the audience, I wanted to kind of go in a little more detail on how we prove this gluing lemma, because it's a little more technical, but I think it's also kind of simple in the end. So the way we prove it is with this very standard mapping from averages over random unitaries to sums over permutation operators. So here, a permutation operator sigma is an operator that acts on k copies of my original Hilbert space, and it permutes those copies in some way. So sigma is drawn from the permutation group on k elements. And there's a very well-known formula for the average of a Haar random unitary to the kth power when applied to a quantum state. And it involves a sum over two permutation elements, sigma and tau, where we first take the overlap of my state with some sigma, and then we output some different permutation tau. And there's some coefficient connecting the sigma and tau, which is known as the Weingarten function. And at first, this formula maybe seems a little complicated, but there's a very simple way to derive it for yourself. And it comes because this Weingarten function, if we view it as a matrix over sigma and tau, it's actually just the inverse of the overlap matrix between the permutations. So if I define some matrix whose elements are like trace of sigma with tau, this is some k factorial by k factorial matrix over the permutations, and its inverse defines this Weingarten function. And then you can kind of easily argue to yourself that this formula for the expectation value of rho is just projecting this quantum state rho onto the subspace of operators that is spanned by the permutations. So that's all this formula is doing. And the fact that we need these funky coefficients is required because the permutations are not precisely orthogonal to one another. This being said, it's known that actually in the limit of large Hilbert space dimensions, different permutation operators become approximately orthogonal to one another. So this is used in lots of works, but it's kind of phrased most nicely in this recent work by Aram Harrell, where he shows that for k squared, much less than 2 to the n, so much less than the Hilbert space dimension, this overlap matrix is approximately the identity. So it's approximately 1 if sigma and tau are equal to one another, and 0 if they're not equal. And because the Weingarten function is the inverse of this overlap matrix, if G is close to the identity, then WG is also close to the identity. And we show in our work, basically using some variant of this fact, that this means that we can approximate the Haar twirl to within very good relative error by a much simpler expression, where we just replace the Weingarten function with the identity matrix. So we trace rho with sigma inverse, and we spit out sigma. So this is very nice. It like drastically simplifies the analysis, and in any application of big random unitaries, we show you can basically always do this. And then once we have this, the gluing lemma follows pretty simply. So we just explicitly write down the formula for the twirl over this multiplied operator of UAB times UBC. So we take the twirl over the first random unitary and over the second. This produces a sum over two permutations, sigma coming from the unitary on AB, and sigma tilde coming from the second unitary on BC. And you can, pretty easily convince yourself the expression has this form. So I trace my input state with sigma on AB and sigma tilde on C. I spit out a permutation that's like sigma on A and sigma tilde on B and C. And then there's one term that kind of connects these, which is trace of sigma with sigma tilde inverse. So this arises where the output of the first random unitary contracts with the input to the second random unitary, which happens on subsystem B. And this coefficient is just the overlap of sigma and sigma tilde on subsystem B. And so again, by approximate orthogonality, this overlap is basically the identity matrix. It basically just sets sigma equal to sigma tilde. And if you set these two to be equal, you get that I trace rho with sigma, sigma, sigma on ABC, and I output sigma, sigma, sigma on ABC. And this is identical to the formula for a Haar random average. And that is essentially the complete proof of the gluing lemma. And each of these steps is true with a small relative error. And the largest error in this approximation comes from when we approximate this trace over subregion B as the identity. And that produces an error that's like k squared divided by 2 to the number of qubits in B.
So this relative error approximation that comes in for free, basically, right? So there's no additional work, and it would not be easier if you just consider diamond norm approximations or so.
No, the relative error is all for free here. Yeah.
Thank you.
Mm-hmm. Okay, and so that essentially completes the proof of the theorem. Once we have this gluing lemma, we just apply it n times, and we get unitary designs. And we have this one additional step that I mentioned in response to Antonio's question to get pseudo-random unitaries. So with just the last couple minutes, I wanted to mention a few immediate applications of our result. But if people have questions on the proof itself, you can feel free to ask them now too.
Okay, just a doubt, maybe I'm missing something. Okay, like relative error is connected to, as you mentioned, this distinguishability between two channels with adaptive queries. Okay, and if the epsilon error is super polynomially small, this implies that efficient algorithms like algorithms that makes polynomial many queries and cannot distinguish the two channels.
Yeah.
Okay, the cryptographic assumptions comes from the fact that you assume other than polynomial mini queries, also the time complexity is poly, or I mean, where the okay.
Where does the so maybe I was a little too brief on the pseudo random unitary part. So to prove that to prove theorem 2, there's 2 steps. The first step is basically follows from the definition that each small unitary is pseudo random. And if that's true, it means that any efficient experiment querying this 2-layer pseudo random ensemble is indistinguishable from an experiment that queries the same ensemble where each U is Haar random. So this is the computational step where we use the cryptographic assumption. We assume that each small random unitary is pseudo-random, so it's indistinguishable from a small Haar random unitary. And then we just need to prove that this construction with small Haar random unitaries is indistinguishable from a big Haar random unitary. And to do that, all of the hard work is already done by our theorem 1, because we have small Haar random unitaries. These are 0 approximate k designs for every possible value of k. And so we get out that this two-layer circuit is an epsilon approximate K design as long as the number of qubits in each patch is at least log nk over epsilon.
Okay.
And then we demand that K is, we demand that this holds for any K superpolynomial in N and any epsilon superpolynomially small in N. And that tells us that the patch size has to be like log, it has to be greater than log times any polynomial in N. And this is true as long as the patch size is at least like polylog. It just has to be greater than logarithmic in N.
Okay, thank you. And also, if I can ask another quick question about possible different constructions with measurements. Do you think for constant depth is achievable with auxiliary qubits and the measurements?
It's a good
Like
question. So I can tell you it's not achievable without measurements. We can show that log n is a lower bound if you just do a unitary circuit. I don't know with measurements.
Because there is the Bravi. I mean Bravi. There is a Bravi paper that shows how to make a Clifford with constant depth auxiliary. I mean, okay, and this would, and then also the paper of Jonas, Saferkamp, and Jens showed how to make T-gate. I mean, doping gives T-design. I mean, combining these two, I mean, do you think that give constant depth or? I mean, Bravi's papers, I think, use auxiliary qubits and feedback.
It's a good question. I will say that in Jonas and Jens's paper, they don't get relative error. You get very good additive error, but I think we tried to kind of use it, but it turns out that once you ask for relative error, you need linearly many T-gates. And I think you can convince yourself this is necessary.
It's necessary. Okay, you say that it's necessary to.
I think so. It's been a while since I thought about it.
I fear this is right. I think this is true. It's not fully obvious how then to combine these tools, although it's a wonderful question.
Yeah. Well, I mean,
So
you might not care about relative error for every application, but we do. Most of our results work with relative error, so you'd have to also extend them to additive error.
Can I ask, you have this kind of two-level brickwork structure effectively, which I guess basically comes from wanting the gram matrix to be diagonal means you need to make it in these blocks. That seems right like more of a mathematical tool than anything that's actually necessary, but probably it would also work just with arbitrary random gates, but you wouldn't really be able to handle the gram matrix.
Yes, that's also our guess. Yeah, we basically the analysis becomes very nice and simple when we kind of coarse grain in this way, where we consider these like big blocks and just depth 2. But if you kind of lost the walls between these blocks, you just did a log depth local random circuit, my guess would be that all of the same scalings hold, but it might be a lot harder to prove. I think Jonas actually told me recently that for 2 designs, it was easy to prove. It followed from an existing paper by Nick Hunter-Jones on anti-concentration in log depth. But for higher designs, they didn't know how to prove it.
By the way, speaking of constant depth, I think that if we prepare, for example, cluster state and doing like measurement-based model computation, then it's create, of course, K design by constant depth and with big anciers. So I think one construction and some deep thermalization argument is also like this sense. So I think it's at least one example of constant depth, but it's not so natural.
Yeah, that's a good point. Although I've never understood this, but with the deep thermalization tricks, you only get one, like the random unitary you get, it depends on your measurement result, right? And so you can only draw each random unitary once, not K times, I guess.
Yeah, so
Okay, yeah, so it's yeah, it gives you some kind of access, but maybe it depends on the circumstance whether that access is good enough for you.
mhm.
But yeah, that's a very good point. Okay. Yeah, I guess we're running a little over time, but I'll just briefly mention a couple immediate applications of our result. So the first goes back to this idea of classical shadows for fidelity estimation. So the original shadows protocol requires a random Clifford unitary, which in 1D requires at least linear depth in n to implement. But after this original shadows paper, there were a few really nice follow-up works, including one by your group, which suggested that maybe you can do just as good, with much lower depth random Clifford circuits. And it was even conjectured in some of these that log depth might be the optimal depth. And our results basically just rigorously confirm this. So we show that log depth random Clifford circuits form unitary 2 and 3 designs. And then we show that approximate unitary 2 and 3 designs are all you need for classical shadows. They give performance that's identical to that of a true 2 or 3 design.
If I may say, that even was used in the last part of the error mitigation no-go theorem, where we used that for the right-hand side on Faunus lemma, we had to show that log depth quantum circuits, Clifford circuits, are unitary 2 designs or approximate 2 designs.
Oh, really? I see.
Mhm.
I see. Yeah, and yeah, this already follows again from those earlier shallow shadows paper. But if this is true, it means that shadows can be implemented at much larger scales than previously known at current noise rates, simply because the number of gates in a log depth circuit is much less than the number of gates in a linear depth circuit. A sort of more surprising result of our work concerns the question of how easy is it to learn the phase of matter of an unknown quantum state. So say I give you a quantum state rho, and I tell you it's the ground state of some local Hamiltonian. And I ask you, does this ground state have trivial order or topological order? But I don't tell you many details about the state rho. So a consequence of our results is that answering this question is actually quantum computationally hard, at least once the correlation length of that ground state is greater than polylog in n. So the topological order is very well defined as long as this correlation length is sub-extensive in the system size. And our result basically shows as soon as it's just a little bit big, like polylog in the system size, it becomes very hard to tell whether a state has topological order. And
As you currently only mentioned unitaries, there's not
Yeah.
a state application. What's the, like, how does this translate and what's the?
Yeah, perfect. So it's the picture I'm showing here. So consider two ensembles of states. One is a product state, the all zero state, and then I apply a shallow 2D random circuit to it. So a shallow 2D pseudo-random unitary. And now because this unitary I apply is pseudo-random, like our theorem 2 showed, the state ensemble I get when I apply that random unitary to the all zero state is a pseudo-random state ensemble. So it's indistinguishable from the Haar random state ensemble. But now I can do the same thing where the initial state is the toric code state instead of the product state. And this produces a pseudo-random ensemble of states that all have toric code topological order. And now because each ensemble is pseudo-random, I cannot distinguish the trivial order ensemble from a Haar random state, and I cannot distinguish the toric code ensemble from a Haar random state, and therefore I can't distinguish them from each other. And so the question of classifying the topological order of these states that we construct is quantum computationally hard. I do want to emphasize that this is in some ways a worst case statement. We construct some example of states where the order of the state is very hard to learn. And it's a very non-trivial and I think open question whether this extends to the states that we see in the real world, which are typically ground states of fairly simple two-local Hamiltonians.
This is also a cryptographic assumption, right? You need to use pseudo-random with being true. You can't use the unitary design.
Yes, yes. To prove all of these learning hardness bounds require the pseudo-random construction. Yeah. And then a very, oh yeah, yeah.
Sorry, just maybe like if you don't care, if you care just about sample complexity, then your result gives something new, or like some epsilon nets argument already suffice. I mean, like a computation of pseudo-randomness when you want time efficiency. But if you care just about samples, I mean,
Yeah. I think this is also not known if you just care about samples, but we haven't thought about how much stronger you can make it if you just care about samples and not efficiency. Yeah,
okay.
we haven't
Because
thought.
if you have this relative error design, you require epsilon superpoly. This says that they are indistinguishable by possibly inefficient time sample efficient quantum algorithm, right?
I'm not immediately sure that because you have a K design, but it's only for some finite value of K. And you're asking about experiments that can query any polynomial number.
True.
So it's not immediate. There are some tricks people have for showing like if you're a K design, but you only have measurements to like one copy of your state at a time. Sometimes you can go from K design to indistinguishability over very large numbers of experiments. But they don't work for any state. Like they require some assumptions on the state. Yeah. So yeah, we thought about it for a little bit, but once we had this pseudo-random part, it was just much stronger. And so one last application, which is again kind of in this quantum learning theme, is the power of time reversal in quantum learning. So as I mentioned, the definition of pseudo-random unitary and unitary design concerns experiments that query a unitary U some number of times. And we show that for such experiments, you can't distinguish a low-depth U from a very high-depth Haar-random U. But a really, really simple thought experiment shows that our ensemble can be distinguished from Haar-random by experiments that query both U and its inverse, U dagger. Essentially, once you have the inverse, you can just measure light cones. And then you can see that our construction has a very small light cone, whereas a Haar-random circuit has a very big light cone. So this is just OTOX, which people have studied in physics for a long time now. And so this actually leads to like an immediate corollary of our result, which is that quantum experiments that have access to time reversal can probe properties of dynamics, so properties of U, that are exponentially hard to detect in any possible experiment without time reversal. And the simplest example of this is just distinguishing whether our ensemble is Haar-random or not. So distinguishing the depth of a quantum circuit. But we show that there's also like other kind of cute examples you can construct that might be very physically relevant. So for example, to distinguish whether some unitary U was generated by short-range dynamics or long-range dynamics, once that U is a certain depth, this can be hard to do without time reversal, but easy to do with time reversal. And we show this again by kind of showing that these look like unitary designs, so they're indistinguishable without time reversal, but then with time reversal, some very simple light cone arguments can distinguish these types of dynamics. So yeah, I think this kind of rigorizes maybe some intuition from the OTOC community in physics the last 10 years. But I think this, this separation can hold in some very physically motivated learning problems. So it might be nice to keep in mind. And so that's all I have. The summary, again, is just that shallow quantum dynamics can very rapidly become indistinguishable from deep Haar random unitaries. And fundamentally, this is kind of allowed by the abundance of non-commuting observables in big quantum systems. There's lots of open questions. I can talk more about them if people are interested, but since we ran a bit over, I'll just stop now and open up for any more questions.
Wonderful. That was great. Yeah, we had millions of questions along the way, but I'm sure there's more questions.
Yeah, if there are more questions, please go ahead.
So if you allow for you dagger axes, then basically the old results were optimal. Is that correct? You need order n times k.
Yes, in 1D. Yeah, so the old results are optimal. They don't actually show this, but there's a very short step you can do from like the Brandau-Horodecky result to show that this U dagger indistinguishability. But there's actually an interesting open question, which we're working on now, which is if you want indistinguishability with respect to U dagger, but you have all-to-all interactions, can you do much better than linear depth? Can you get log depth with all-to-all interactions?
For designs or for pseudo-random?
For both. It's actually for design. Yeah. So this is work in progress, but
So the idea is just to break the light cone argument by having all connectivity.
Exactly. So when you have U and U dagger, you're always limited by this light cone argument. So all of the best things you can do are kind of very intuitive. It's linear in 1D, log in all-to-all. But we don't know how to get the log yet. I think we've probably figured it out. But yeah, that was a rather non-trivial task. And the reason why, sorry, just a brief comment. The reason why like all these previous results have linear depth is because when you use these spectral gap methods to bound the error in a design, there's always a kind of final step when you translate the spectral gap to the experiment you care about that has some large dimensional prefactor, like 2 to the n. And to suppress that, you normally have to take your error to be exponentially small, like 2 to the minus n. And this always gives some linear overhead in your depth. So yeah, in some ways, like with spectral gap methods, you can get everything you want in linear depth, but improving in any aspect to get like log depth or log depth, you always need to come up with some new tricks that go beyond the spectral gap. Yeah.
Sorry, there's like different like Oracle access models that make use of U and U dagger. I mean, like is it fair to say that one of the lessons from your work is also that having access to U dagger is just very powerful as an Oracle access?
Yes. It's exponentially more powerful than just having U for certain questions.
Okay, thanks.
Yeah. Mm-hmm.
How do you capture scrambling dynamics in the definition of a unitary design?
This is actually exactly what we've just been talking about. So,
sorry, sorry if I missed that.
No, I didn't. No, sorry, I didn't say that. That was what we're talking about. But, so scrambling, like one of the features we associate with scrambling is the decay of OTOX, which quantifies like operators and how they spread. And the only way to measure these is in experiments with time reversal. That's now kind of like rigorously established by this work. And so, yeah, for me, it was like disappointing at first when I learned that unitary designs did not capture OTOX well at all. Like you can have something that's an extraordinarily good unitary design, and it just completely fails to capture OTOX. And so, yeah, what we're thinking of is kind of just writing down a new definition of unitary design that captures both experiments that core U and ones that have U and U dagger. and then trying to construct unitary designs with optimal depths under this definition.
Right. Is capturing the idea of the decay of the OTOC the same as having some type of, as requiring some type of light cone or something like that? Like, is it, if I think of scrambling as sending your information all over the place, does this definition also guarantee to me that you're scrambling information all over the place, like in some geometric sense? I don't know if that makes sense.
Yeah. I mean, definitely the OTOC, like if the OTOC has decayed everywhere, it is a signal that you're, at least in some metric, your information is all over the place.
Yeah.
And if you have, we're calling it like a strong 2 design, but if you have a strong 2 design that's robust to you and you dagger, you can say the OTOC's decayed everywhere. But then, yeah, there's also kind of like more fine-grained aspects of this, like what do experiments with you and you dagger at higher K probe? And there, I think it's like, it's a lot less clear, at least to me, whether all you need is a big light cone or, you know, kind of what you need to get these strong designs for very high K. And so that's what we're trying to prove now. But yeah, for just like the 2 design case, it's just light cones, basically.
Nice.
Is the obstacle that you have with this all-to-all connectivity that you want to find, if I imagine all the qubits and you've got K local unitaries, is the obstacle that you want to find a construction which contains all the possible combinations of unitaries on the different qubits? Or did I get that wrong?
What do you mean by contains all the combinations of unitaries?
I mean, the question I have in mind is how many layers do I need to get the following thing? I want to have contained all the possible K local things, and I want to minimize this number of layers. I mean, intuitively, I could get a, what is it, n to the K or so if I just put 1 unitary per layer. But what you want to show here is that you just need log n many layers, right? Or is it a different?
Yeah. This is related to the question I had earlier, like how flexible that kind of gluing is somehow to play with like circuit topology or so. That's a very good question.
Okay, because I think I have something which does this in, I mean, it's K squared log K log n to get this construction.
To get what construction?
To get this, to answer the question how many layers you need. It's called perfect hash functions, perfect hash family construction or so.
Okay. I'm not sure I totally understand what you're getting with the perfect hash family, but I'd be happy to talk more, maybe like right after or anytime.
Yeah, sure. Yeah.
Okay, well, I think there are no more questions. So thanks a lot for the very nice talk and also for the very nice work. And yeah.
Yeah, thanks also for